Hello, and welcome to my talk on how do black holes form, developing a statistical tool to analyze gravitational waves with future detectors. I am Divjyot Singh, and this is the work I did during my time at MSRP and in association with the LIGO group. LIGO, or Laser Interferometer Gravitational Wave Observatory, is an extremely precise instrument that measures gravitational waves, which are disturbances in space-time, coming from deep outer space. When two black holes in space collide or merge, they release a huge amount of energy in the form of gravitational waves. These wave signals carry a property called redshift, which tells us how long of a distance these waves have traveled and how much time they took to reach us. The black holes that form these signals can themselves be formed in multiple ways. Two of which in particular are primordial black holes, which were those formed soon after the Big Bang, and population 3 stellar black holes, which were formed from the oldest stars with virtually no metal content. The primordial black holes is something that Stephen Hawking did a lot of work on, but hasn't been proven to exist yet. By knowing more about primordial black holes, we can answer a lot of mysteries about the universe, including dark matter. Let's take a look at this graph. On the x-axis, we have the age of the universe, and this point being 13.8 billion years being the current age of the universe. And it goes all the way back to about 100 million years on the log scale. On the y-axis, we have the merger rate, which represents the total amount of black hole mergers per unit volume per unit time. The current detectors have a limit, and as you can see in this limit, we cannot see any interesting trends. The trends being observed here are the blue line is the population 3 black holes, the orange line is the primordial black holes, and the green line represents the total, which is the signal that we observe using LIGO or other gravitational wave detectors. To be able to understand the signal or study it, we need future detectors which can go all the way back to 100 million years and observe these interesting trends. But why do we want to understand these? The total trend that we get, if we can figure out whether primordial black holes are part of that total data, it can help us investigate whether or not they exist. So to do that kind of analysis, I used Bayesian statistics, which is based on the Bayes theorem. And I wrote two models, one which had both primordial black holes and pop3 black holes in it, mixed in the ratio F, and another one which had only the population 3 black holes. And then I simulated some gravitational wave data using the first model, and then tried to fit it to both of my models. The results that I got are shown here. So as you can see, for model 1, here is the probability distribution that we got for the different parameters of the model. And you can see, and the blue lines represent the true values of the model. And you can see that the distribution is roughly centered around these true values. However, for the second model, the true values don't even show up in the plot, and the distribution is very off. If we look at the evidence values, which is a number that tells us how good of a fit a model is to the data, you can see that the first model has orders of magnitude higher evidence than the second model, which gives us a Bayes factor of about 10 to the 9, representing that the first model is a much better fit for our data. So we concluded that model 1 is more favored over model 2 for the simulated data, and that this technique can successfully investigate the presence of primordial black holes in BBH data that we would get from future detectors. I would like to acknowledge the MIT Summer Research Program for funding me, and my fellow MSRP interns and pod leaders for supporting me. Thank you.